Imagine you step into a time machine, you dial the controls back to the year your grandparents were young, and suddenly, with a flash of light, you arrive decades in the past. You walk the streets of history, blending in with the world of another era. Now imagine, by accident or intention, you interfere with a small event. You prevent your grandfather from ever meeting your grandmother. In that instant, a terrifying question emerges. If your grandparents never met, you were never born. But if you were never born, how could you have traveled back in time in the first place to stop them from meeting? This is the essence of the time paradox, one of the most haunting mysteries in science, a problem so profound that some physicists believe it might prevent time travel from ever being possible. Time paradoxes are not just quirky riddles from science fiction. They cut to the heart of physics, logic, and reality itself. They raise terrifying questions. Can the past be changed? If it can, do we risk unraveling the entire fabric of existence? And if it cannot, then what is the true nature of time? Today, we'll dive deep into the enigma of time paradoxes, exploring why they terrify scientists, what modern physics says about time travel, and whether the universe has safeguards that prevent reality from collapsing under its own contradictions. For most of human history, time was seen as a simple, steady river, flowing inexorably from the past through the present and into the future. Aristotle described time as the measure of change. Isaac Newton believed time was absolute, ticking uniformly for everyone everywhere like an invisible cosmic clock. In this view, paradoxes were unthinkable because time could never loop back. But in the early 20th century, Albert Einstein shattered that view with his theories of relativity. Special relativity revealed that time is not absolute. It stretches and contracts depending on how fast you move relative to the speed of light. General relativity showed that gravity itself bends time, slowing clocks in strong gravitational fields. Suddenly, time was no longer a rigid arrow but a flexible dimension intertwined with space. In Einstein's equations, paths through spacetime could, in theory, bend back on themselves, creating closed, timelike curves, routes that allow you to return to the past. This possibility transformed time paradoxes from fantasy into genuine scientific problems. If the laws of physics permit travel into the past, then paradoxes cannot be avoided unless some deeper principle intervenes. The most famous and frightening example of a time paradox is the grandfather paradox. Imagine traveling back and killing your grandfather before he has children. That act erases your own existence, which means you could not have traveled back in time, which means your grandfather was never killed, which means you were born after all. The logic loops endlessly, with no resolution. Scientists fear this paradox because it suggests contradictions that break the very consistency of reality. In physics, one of the most sacred principles is causality, the idea that causes precede effects. A paradox violates causality, creating effects without causes or causes without effects. If paradoxes can exist, then the universe itself becomes unstable, a place where logic collapses. This is why some scientists argue that time travel into the past must be impossible, not because the equations forbid it, but because paradoxes would destroy the coherence of reality. Another equally disturbing paradox is the Bootstrap Paradox, sometimes called a causal loop. Imagine you travel to the future, find a book containing advanced scientific knowledge, bring it back to the past, and publish it under your own name. Centuries later, you discover the same book in the future and repeat the cycle. The knowledge in the book exists, but it was never created by anyone. It loops endlessly, trapped in time, without origin. This paradox terrifies scientists because it challenges the principle of conservation of information. In physics, information cannot be created or destroyed. It must have a source. The Bootstrap Paradox seems to defy this rule, suggesting that objects or ideas can simply pop into existence without a cause. If such loops are possible, then the boundary between reality and fiction collapses, and we lose the ability to define what is real. Not all paradoxes are contradictions. Some are counterintuitive but perfectly consistent with physics. The twin paradox from Einstein's relativity is one example. Imagine identical twins. One stays on Earth while the other travels near the speed of light and returns. The traveling twin finds that less time has passed for them compared to the twin on Earth. They are younger. This is not science fiction but a proven effect of time dilation, confirmed by experiments with atomic clocks on airplanes and satellites. The twin paradox shows that time is relative, dependent on motion and gravity. While it doesn't create logical contradictions, it demonstrates that our everyday intuition about time is deeply flawed. If even a journey at near light speed can alter time, what would happen if space-time itself could be bent into loops? The door to paradoxes opens wider. One of the most discussed mechanisms for time travel is the wormhole, a hypothetical tunnel connecting two distant points in space-time. Einstein and Nathan Rosen first proposed the idea in 1935, calling it an Einstein-Rosen bridge. Later, physicist Kip Thorne showed that if a wormhole could be stabilized with exotic matter, it might allow travel not only across space but also through time. In theory, if one end of a wormhole is moved close to a black hole or accelerated near the speed of light, time at that end would slow relative to the other. Traveling through the wormhole could then allow you to arrive in the past. This is where paradoxes emerge in their most terrifying form. A wormhole time machine could let you go back and interfere with your own timeline, creating contradictions. Wormholes are permitted by Einstein's equations, but the paradoxes they create suggest that perhaps nature forbids their use as time machines. The possibility of paradoxes worried even Stephen Hawking, who proposed the chronology protection conjecture in 1992. Hawking suggested that the laws of physics themselves prevent paradoxes by forbidding time travel to the past. He argued that quantum effects would cause wormholes and closed timelike curves to collapse before they could be used, protecting the consistency of history. In other words, nature has a built-in safeguard against paradoxes. Hawking even joked that the absence of time-traveling tourists from the future is evidence that time travel is impossible. While no experiment has confirmed or disproved this conjecture, it remains one of the strongest reasons many physicists doubt that paradoxes can ever manifest in reality. Some physicists offer a different solution. Paradoxes may be avoided not by forbidding time travel, but by splitting reality itself. According to the many worlds interpretation of quantum mechanics, every quantum event branches into multiple parallel universes. If you travel back in time and kill your grandfather, you don't erase yourself. You simply create a new timeline where you were never born, while the original timeline remains intact. In this way, paradoxes are avoided because every action creates a consistent history, just in a different universe. This idea has been popularized in science fiction from Avengers: Endgame to Rick and Morty. But it raises disturbing questions. If every possible action creates a new universe, then reality is an infinite multiverse, endlessly branching with every decision. We avoid paradoxes, but at the cost of multiplying realities beyond comprehension. Another proposed resolution is the Novikov self-consistency principle, named after Russian physicist Igor Novikov. This principle states that if time travel is possible, events must be self-consistent. In other words, if you go back in time, everything you do must be consistent with history as it already happened. You cannot kill your grandfather because your existence proves you didn't. If you try, something will always prevent it: a jammed gun, a missed shot, or an unexpected intervention. According to this principle, paradoxes are impossible because the universe self-corrects. Time travel may be allowed, but free will is not. This solution terrifies some because it implies that even if you had a time machine, your actions would be constrained by the logic of history. The universe would conspire to preserve consistency, and your choices would not be your own. In recent years, physicists have explored time paradoxes using quantum mechanics. Some theoretical studies suggest that closed time-like curves, mathematical loops in space-time, can be simulated using quantum systems. In 2014, researchers at MIT and the University of Queensland studied how quantum particles behave when sent back through simulated time loops. Surprisingly, the particles always emerged in a way that avoided paradoxes, as if quantum mechanics itself enforced consistency. Quantum computers, too, have been used to model paradoxes, showing that information can be preserved without contradictions. These results suggest that if time travel is possible, quantum laws might prevent paradoxes automatically. But the research remains theoretical, and no experiment has yet created a real paradox or proven that time travel is feasible. Why do paradoxes terrify scientists so much? Because they undermine the very foundation of physics: causality. Science depends on the assumption that the universe follows consistent laws, that causes precede effects, and that contradictions do not exist. A paradox breaks all of these rules. If paradoxes are possible, then science itself collapses. Predictions become meaningless, logic breaks down, and reality becomes unstable. This is why many scientists believe paradoxes are nature's way of warning us. Time travel into the past may be mathematically possible, but it will never be physically realized. Others argue that paradoxes reveal gaps in our understanding, clues that we need a deeper theory of quantum gravity, to reconcile relativity and quantum mechanics. Either way, the terror of paradoxes lies not just in their bizarre scenarios, but in their ability to expose the limits of human knowledge. The mystery of time paradoxes forces us to confront the deepest questions of existence. Is time a line, a loop, or a branching tree of possibilities? Can the past be changed, or is history fixed forever? Are paradoxes impossible because the universe forbids them? Or do they exist in realities beyond our perception? These questions terrify scientists because they touch the edge of what we know, challenging both logic and physics. And yet, they also inspire us. The fact that paradoxes emerge naturally from our equations shows that time is not what it seems. Perhaps one day, with a theory of quantum gravity, we will understand whether paradoxes are truly impossible, or whether reality is far stranger than we can imagine. Until then, time paradoxes remain the greatest warning sign on the road to time travel. Proceed with caution, for beyond lies a realm where cause and effect collapse into madness. So are time paradoxes real? We don't yet know. They remain one of the most terrifying and fascinating mysteries in science. From the grandfather paradox to the Bootstrap Paradox, from wormholes to quantum computers, the question of paradoxes forces us to confront the very nature of time itself. Thank you for joining me on this journey into the haunting enigma of time paradoxes. If this exploration fascinated you, please tap the like button, subscribe to beyondx, and ring the notification bell so you never miss another deep dive into the mysteries of physics and the universe. Together, we will keep chasing the greatest questions of existence, exploring the strange edges of reality, and seeking answers to the mysteries that terrify even the most brilliant scientists.